Okay, friends, happy Wednesday morning. Let's see, we're entering a part of the course where we're going to need to be flexible with the syllabus. So I intended to finish metabolism on Monday, and it turns out we're not even going to finish it today. So sorry. Let's see. So we'll need to be just flexible as we adjust things. Obviously, I'm not going to hold you responsible for things I don't teach you that were on the syllabus. Let's see. Common question about the final. We already addressed that last time, but I'll just say the final is comprehensive and cumulative. It's not exhaustive. I can't ask a question about every single topic. It's a final that I write. And what else? Oh, what percentage will be on this last stuff versus the previous stuff? Some amount. Probably maybe more on the last stuff than on the previous stuff, but by that I don't mean 50, greater than 50-50, just some. How many questions? Probably more than 20. It's a 250-point exam, so you can expect to encounter more questions. Nevertheless, it should be doable in about the amount of time you typically allotted for a final. However, it will not be given in class. You're going to take it at the testing center anytime you want during finals week. Some people love that. Other people hate that because if you have to show up on a certain day, at least it's over and then you can not worry about it. But that's sort of what we're going to do. Okay. We've gotten to the point where we're done with glycolysis and we've made pyruvate, and that has allowed us, and we've got 2 molecules of pyruvate for every molecule of glucose that we used. And our goal now is going to be to oxidize all of those carbons to the level of CO2 and to generate as much NADH, FADH2, and ATP as we can during the process. But first, we have to get to the key intermediate in a lot of metabolism, which is acetyl-CoA. And so how are we going to get from pyruvate, which has 3 carbons, to acetyl-CoA? And just to emphasize the point, there's the 2 carbons in acetyl-CoA, and this is where they come from in pyruvate. Some interesting features of pyruvate are that it is an alpha keto acid. And an alpha keto acid is different from a beta keto acid. I should point out too that we're going to lose this carbon as CO2. So of the stuff you're currently exhaling, some of it comes from this process. Now, the problem is we've done CO2 reactions before, reactions that generated CO2 before. You might remember we called those decarboxylation reactions. But the challenge is we always did that not with an alpha keto acid, but with a beta keto acid, which we don't happen to have here. In a beta keto acid, if you do a decarboxylation reaction and what you kick off as a leaving group here is an enolate, a resonance stabilized enolate, with a negative charge on the alpha carbon and delocalized on the carbonyl oxygen. But we don't have that situation here. In fact, if we attempted to do a decarboxylation on an alpha keto acid, what we would end up with is a really, really unusual intermediate that would have a negative charge on a carbonyl carbon. And that is not resonance stabilized. And that is not an enolate. you see the difference between the enolate here on the left that we get from decarboxylation of a beta keto acid, resonance stabilized, whereas this one on the right, decarboxylation of an alpha keto acid, gives us something that's negatively charged on the carbonyl carbon. That's totally different. So far, in all we've done, we've used the alpha carbon as a nucleophile and the carbonyl carbon as an electrophile. And here we're saying in order to get this reaction to work, we're going to have to somehow use the carbonyl carbon as a nucleophile. That's going to be challenging, and that's going to involve an important cofactor called thiamine pyrophosphate ylide. We'll abbreviate that as TPP. And it's going to involve another important group called lipoate, because if you look at what happens in this reaction, not only do we break a carbon-carbon bond, but we replace that carbon-carbon bond with a carbon heteroatom bond. So this is actually an oxidation reaction. We call this oxidative decarboxylation. And this is going to be catalyzed by the Pyruvate Dehydrogenase complex. And this has 3 different enzymes that catalyze the reactions that lead from pyruvate to CO2 and acetyl-CoA. So let me just show you the players. TPP stands for thiamine pyrophosphate ylide. You've heard pyrophosphate before. You've heard ylide before. An ylide is simply a molecule that has a positive and a negative charge on adjacent carbons. So here's the structure of the thiamine pyrophosphate ylide. That's the pyrophosphate group. This nitrogen's attached to something else, and this ring, the ring to which it's attached, looks kind of like a pyrimidine. But fortunately, the business end of the molecule is all right here. I should add that this is the conjugate acid of thiamine ylide, and the thiamine ring here is aromatic, which means this CH bond is held perpendicular to the plane. I'm sorry, the CH bond is held in the plane of the page, but perpendicular to the pi system. But the pKa of this proton is such that it can be removed by a base, and the lone pair that is left behind would be in an sp2 orbital orthogonal to the pi system, and it's going to be nucleophilic. Okay, so that's thiamine pyrophosphate. We're going to see this be both a nucleophile, and we'll see it also being a leaving group, and that has to do with the fact that the pKa of its conjugate acid is relatively low. Okay. The next structure, the next player that's important is called lipoate. And this is kind of weird. The lipoate group takes advantage of the innate redox capabilities of sulfur. When we talked about amino acid side chains, we talked about how cysteine sometimes forms disulfides, and that disulfides are an oxidized form of thiols. So this strange group this portion is called lipoate. And then this, what I've drawn over here, is actually a lysine residue from the pyruvate dehydrogenase complex. So you can tell it's lysine because you've got alpha, beta, gamma, delta, and epsilon carbons, and then there's a nitrogen. So that used to be an amino group, but we functionalized it as an amide with this other group called lipoate. And this is going to be our oxidizing agent. And just to review a bit about disulfides, imagine you have two cysteine residues in a protein, and I'm just gonna, there go the side chains, and you add oxygen. You can do this with just oxygen from the air, and it happens spontaneously. Look at what we have lost in this process, okay? We have a proton, and then we have a hydride. And formally, you could imagine this reaction occurring as a base removes this proton, and then this one attacks the sulfur, and then hydride gets delivered somewhere. That's not actually what happens, but that's how you can tell that this is an oxidation process, because whereas we had two protons and two sets of lone pairs before, now we've lost those two protons and we only have two of those electrons. In a way, you can think of this as an oxidation reaction where we lose a hydride and a proton. Okay, so the thiol form is reduced. The disulfide form is oxidized. And of course, something that's oxidized can reduce something else. Just like NAD+, which is oxidized, can did I get that wrong? I got that totally wrong. Something that is already oxidized can oxidize something else, and in so doing, it itself gets reduced. You'll see in just a second. So the parts of these molecules that I'm going to draw for you in the future mechanisms are highlighted here. So we'll need this portion, and then we're going to need sort of this portion. I'm running out of cool colors to use. That's still pink, isn't it? All right, so let's go ahead and begin with the first step of this process. And this is catalyzed by a subunit of the PDC called Pyruvate Dehydrogenase. Okay. So you've got pyruvate here, and it's got a ketone, and that ketone should be electrophilic at the carbonyl carbon, right? And then I told you that the thiamine ylide is nucleophilic at the carbon in between the sulfur and the nitrogen, the one that's negatively charged. Okay, so we're going to have nucleophile attacks carbonyl. This is stuff we've been doing since the very beginning of this class. We break the pi bond and make a tetrahedral intermediate. Now, to save us time, we could go ahead and draw that tetrahedral intermediate with the negatively charged oxygen. But to save ourselves some time, we will instead show that negatively charged oxygen getting protonated in the same step. And the product of that step is an alcohol. And this is exactly what you would expect for nucleophilic addition of a ketone, of a nucleophile to a ketone. Okay, and so yeah, this mechanism is nucleophilic addition to a ketone. And in this process, I want you to pay attention to how these reactions are similar to things that you've seen before. The players are different, but really this shouldn't look a lot different to stuff we did way back for the first exam. Okay, so try to see the similarity. All right. Now, the reason we did that isn't maybe clear right now, but I'm going to redraw this molecule in a way that hopefully communicates the usefulness of adding the thiamine ylide to this molecule. Okay. Notice this carbon here used to be before the reaction, it was our carbonyl carbon. Right? Now, that got turned into an alpha carbon to both this group here and this group here. Also notice that whereas before, relative to the CO2 group, if we go back to pyruvate and begin labeling with the carboxylic acid, our ketone was on the alpha carbon relative to the carboxylic acid. But now that we've added thiamine, notice what we've got on a beta carbon now. And that should start to look similar to a beta keto acid. All right. And what do we do with beta keto acids? They can decarboxylate because the thing that's left behind is resonance stabilized, right? Okay, so thiamine, the purpose of adding thiamine ylide is it converts the pyruvate, which was an alpha keto acid, into something that resembles a beta keto acid. And this is now primed for decarboxylation. All right, so how are we going to do that? Well, we take electrons on the oxygen, they kick down here, and then we have the electrons from the carbonyl carbon to alpha carbon bond go on to the alpha carbon. So there, we've just lost our first CO2. And let's now draw what's left behind. Do you see how what's left behind resembles what's left behind, the enolate that's left behind when you do decarboxylation of a beta keto acid. Because this is an enolate, basically. It's got a resonance structure in which I can delocalize, in which I can move the negatively charged, I can move the lone pair on that alpha carbon to now be a pi bond. And then my nitrogen can be neutral, right? I can basically do this. So this is resonance stabilized, and therefore it's enolate-like. So that means we can use it as a nucleophile. But I want you to pay attention to which carbon is nucleophilic. Remember, before I told you that if we did decarboxylation of an alpha keto acid, we would have something that's nucleophilic on a carbonyl carbon. We've basically got that going on here. This was our original carbonyl carbon, and now it's nucleophilic. But the reason it can be is because of the presence of the thiamine group. All right. What happens next is the oxidation step. So this step involves our disulfide. The nucleophilic carbon will attack this sulfur, and then that will break the sulfur-sulfur bond, and the other sulfur that leaves will pick up a proton. And the product of that step is this. All right. And in this step, you can see that the disulfide got reduced to thiol and another thiol. And this carbon that was negatively charged got oxidized because it didn't used to have, it only had one bond to a heteroatom, and now it has two. All right. So if you remember that we've said we're going to use, sorry for getting that wrong, we're going to use the thiamine ylide as both a nucleophile and a leaving group. We're ready now to do an elimination reaction from a tetrahedral intermediate. A base removes this proton, electrons kick down, leaving group leaves. This is a lot like acetyl hydrolysis. And that regenerates TPP ylide as a leaving group, which I'm not going to draw again. And then we make a thioester, in which the two carbons from pyruvate are now here, and instead of being at the ketone, they're at the oxidation state. And this is sometimes called acetyl dihydrolipowate, because before it was lipoate and it got reduced, and the reduced form is called dihydrolipowate. So we've made a thioester. Okay, questions about that? Yes?
Is there a reason why it attacks at the sulfur that's closer to the argon?
Is there a reason why it attacks the sulfur closest to the R group? I looked it up, and it does. I'm not sure why. And I actually don't know how well they know that it's this one. It certainly would work if you did the other one. And frankly, Thioester Exchange is really fast, and it would be an intramolecular reaction to be swapping this acetyl group back and forth between these two. So I think I just picked one, actually. Yeah. Okay, what else? Okay. In all of this, look for similarities to things that you've seen before. All right. The next step is easy, and we don't actually need to draw the mechanism too much. This is Thioester Exchange. Or you could call it Trans-Thioesterification if you wanted to use an Asian word and sound like a bureaucrat. So here we're going to add the coenzyme A thiol. I haven't drawn the structure for that for you, and I probably won't. It's interesting, but a detail we don't need to deal with. The enzyme subunit of the PDC that catalyzes this process is called Dihydrolipowel Acetylase, because it's going to transfer the acetyl group here from this thiol to the coenzyme A thiol, and it's going to release dihydrolipoate as a leaving group. And the mechanism here is just nucleophilic acyl substitution. That is, you will take, and I think there was a question on this on your first exam, you'll have a base, remove a proton here, the thiolate attacks the carbonyl carbon to give a tetrahedral intermediate, electrons kick down, and the other thiol leaves. Energetically, this should be sort of neutral, trading one thioester for another. The thing that will drive it forward is we're immediately going to reoxidize this dihydrolipoate so that we can crank through another reaction. But this is the point at which we've made our precious acetyl-CoA intermediate, where also we've funneled the carbons of fatty acids, and we will take this acetyl-CoA and take it into the citric acid cycle. The third step, we're not going to draw the mechanism of it. The mechanism is known and it's complicated, and we could talk about it, but I don't really think it's worth our time. If you want to know more about it, you can come ask me and we can look at it in my office. But what basically happens is you take NAD+, and you use, you need FAD as a cofactor. Let's see what else. And the subunit of the PDC that does this is called, unsurprisingly, Dihydrolipowel Dehydrogenase, because dihydrolipoate is the reduced form of lipoate, and dehydrogenase means we're oxidizing it. And that will regenerate the disulfide bond and will also produce NADH. Okay. And with that, we've regenerated everything we need. We have made a molecule of NADH, and that can then go to the electron transport chain, and each NADH can make about 3 ATP. So already I think we're coming out ahead relative to glycolysis. If I recall, in glycolysis we made 2 ATP and 1 NADH, well, I forget, 2 NADH, 2 FADH2 or something like that. So we're making some more profit here, and we've made acetyl-CoA. So any questions you want to ask about that, pyruvate dehydrogenase complex mechanisms, the decarboxylation, the Thioester exchange, and then the reoxidation of the thiol. No? Okay. Good. So now we get to the citric acid cycle. Dun, dun, dun. And this occurs in mitochondria. It's something that we do as eukaryotes that bacteria don't do. And in the citric acid cycle process, we're going to take 2 molecules of acetyl-CoA, 6 of NAD+, let's see, 2 of FAD, 2 of GDP, a couple phosphate ions, and we need water molecules so that we don't later draw just protons hanging out on their own. That's going to generate 2 molecules of CO2, 2 molecules of the coenzyme A thiol, 6 of NADH, 2 of FADH2, 2 GTP, and let's see, 6 extra protons. And each of these NADHs can be exchanged for, on average, 2 ATP molecules. I'm sorry, 3 ATP per NADH in the electron transport chain. That's approximate. It'll depend on efficiency and other things, but that's pretty close. And in the electron transport chain, FADH2 intercepts that a little bit further down due to its lower reduction potential. And so you get about 2 ATP per FADH2. So if we're doing the math from these 2 molecules of acetyl-CoA, we're going to come up with about, and counting GTP as though it were ATP, we're going to come up with about 24 ATP for these 2 molecules of acetyl-CoA. So that's a pretty large yield, and we can go back and compare to what we made from glycolysis, and it's quite a bit more. So chemically, what do we got to do? We've got to turn this thioester into CO2, and we have to turn this methyl group into CO2. Both of those are oxidation reactions. But there's not really great ways to do that directly, and so what we're going to do is we're going to incorporate the carbons of acetyl-CoA into a host molecule, and then we're going to rearrange functional groups on that resulting molecule to get us into a situation where we can do decarboxylation. So our goal for this overall process is going to be to lose 2 carbons as CO2, and then we're going to need to regenerate the host molecule. And remember the ways we can do decarboxylation now. We've done decarboxylation before for a beta keto acid, and we can also do it with an alpha keto acid, provided that we use TPP and lipoate to make things go. All right. I will point out that once we incorporate acetyl-CoA into the host molecule, we completely lose track of which carbons come from acetyl-CoA because the intermediate we make is symmetrical. So it's not really possible to look at the citric acid cycle and say, oh, that carbon came from my molecule of acetyl-CoA. Because what happens is the cycle recycles so many times that carbons change positions. What I mean is it's not going to be really clear if we call this carbon 1 and carbon 2. At a certain point, we're going to lose track of which one's carbon 1 and which one's carbon 2. And at that stage, we'll no longer be able to say exactly where the CO2 came from. If you think about all the possibilities, in some cases, it might take a couple of turns of the citric acid cycle to lose. If you were to like isotopically label acetyl-CoA, it would probably take a few turns of the citric acid cycle to get rid of all of the labeled carbons. Okay, so that's the overview. Let's dive in. So first, we're going to incorporate acetyl-CoA into the citric acid cycle. And the host molecule is a 4-carbon acid, a 4-carbon, 1, 2, 3, 4, diacid with a ketone on the second carbon of the chain. And this is called oxaloacetate. And the mechanism of the reaction is basically going to be two things. First, an aldol reaction, and second, Thioester hydrolysis. So that the product that we get looks like this. And will release the coenzyme A thiol. And this molecule is called citrate, and unsurprisingly, the enzyme is called citrate synthase. Now, look at citrate. Is it a chiral molecule or an achiral molecule or a non-chiral molecule? Is this a stereocenter? No. Why? Because you got two identical things. And this is the symmetric intermediate where we entirely lose track of acetyl-CoA. Because here are the 2 carbons of acetyl-CoA. Here are the 4 carbons of oxaloacetate. You can understand it to have occurred this way, where those 2 carbons came from acetyl-CoA, or you can understand it to have occurred this. No, that's not, that you can't understand it to have occurred that way, sorry. This way, where these 2 carbons came from acetyl-CoA. So, sorry, I know it would be nice to follow acetyl-CoA through this process, but we just lost them. And so we're sort of just stuck, okay? Now, aldol reaction, how does that work? Well, what is usually the electrophile in an aldol reaction? It's usually a ketone or an aldehyde. So, do we have that here? Yes, we have the ketone of oxaloacetate. Do we have in acetyl-CoA an alpha carbon that could be deprotonated to make an enolate? Sure, and we've actually done that kind of thing before. So let's have a base, remove this proton, and then we could draw the arrow here to make the enolate, and then draw that enolate as a separate intermediate. I'm going to avoid that to simplify things, and I'm going to have those electrons going to attack the carbonyl carbon directly. We could push the arrow here to that oxygen to indicate that we would get a tetrahedral intermediate with a negatively charged oxygen. But to accelerate things, I'm going to show the subsequent proton transfer step just right here at the same time. So overall, what have you got in this process? You've got deprotonate to form enolate. You've got the actual aldol reaction, aldol attack, and then you have protonate the negatively charged oxygen. So understand we're just simplifying things and making things faster. Probably this occurs in 3 separate steps. All right, so that's the carbon-carbon bond forming step. And just for simplicity's sake, I'm going to illustrate one of the possible options. Here is the new bond we made. Here is the acetyl-CoA group. And at this stage, this is a chiral molecule, and we could tell which of the 2 carbons were from acetyl-CoA. What happens next is Thioester Hydrolysis, where we're going to lose coenzyme A. And so this is Thioester Hydrolysis. First, and I won't draw the mechanism because this should be pretty easy, a base deprotonates water, which attacks the thioester as a nucleophile. You get a tetrahedral intermediate. Electrons kick down, and the negatively charged thiolate leaves, and as it's leaving, it picks a proton off the new acid you just made to get citrate. All right. Sorry. Okay. Questions so far? All right. Now let's look at the citrate molecule. And let's, again, remind ourselves of our goal. We want to lose 2 molecules of CO2, 2 carbons of CO2, 2 of the carbons of citrate we want to lose as CO2, and we want to regenerate oxaloacetate, and the methods we have for losing CO2 is either regular decarboxylation of a beta keto acid or oxidative decarboxylation of an alpha keto acid. The problem is that let's identify the 3 carbonyl carbons we have. We've got a carbonyl carbon here. So from that perspective, we have the carbon bearing this oxygen is an alpha carbon. We have another carbonyl carbon here. And from that perspective, the carbon bearing the OH group is a beta carbon. And then finally, we have a carbonyl carbon here. And from that perspective, the hydroxy group is on a beta carbon. So if you are thinking about strategy, you could ask, okay, this is great. We have an option to make either an alpha keto or a beta keto acid simply by oxidizing the OH group, right? Wrong. Can you oxidize a tertiary alcohol? Nope. Because remember that oxidizing a tertiary alcohol via NADH oxidizing an alcohol via NADH usually involves a base removing this proton, and then you lose hydride as a leaving group, only it's delivered straight to NAD+. You have to have a hydride on the carbonyl carbon to lose. And if you don't have a hydride to lose, there's no oxidation. So all the first step is done is incorporated the 2 carbons, but we're not in a place where we can attack our goals. So we've got to do some functional group rearranging to get the oxygens on carbons that are useful to us. All right, so what's going to happen now, and we'll call this both steps 2 and 3, is that we're going to convert an aldol product, which is citrate, a beta hydroxycarbonyl compound, right? This is the aldol product of acetyl-CoA adding. And we're going to do what often happens to aldol products, which is we're going to remove a proton from the alpha carbon with some base, making an enolate. And then, after we've made that enolate, the electrons on the alpha carbon are going to kick down and cause hydroxide to leave. This is just dehydration of an aldol product to give you an alpha-beta unsaturated carbonyl compound. Now, I'm drawing just one of the possibilities because, of course, we could have removed this alpha proton and made the double bond here. The intermediate is symmetric, so we're not going to worry about those possibilities. Notice now, this was our, oh, that's my wake-up alarm. Cool. I mean, no, I hate that alarm. Let's see. So we've converted our beta hydroxycarbonyl compound into an alpha beta unsaturated carbonyl compound. And this is just dehydration of an aldol product via this E1CB mechanism where we make the enolate first and then kick off the OH group. The product here is called aconitate, and the enzyme that catalyzes this process is called, unsurprisingly, aconitase. Okay, but we're not done there because this aconitate really doesn't hang around as an intermediate, and this step is reversible, as you well know, for aldol reactions. The beauty of aconitate is that it is an alpha-beta unsaturated carbonyl compound in two directions. Hold on. Okay. So if the OH group that we lost were to come back in and attack yellow beta carbon, we would just end back up with citrate. And that happens all the time. But if alternatively OH hydroxide attacks blue beta carbon, that's going to move the OH group from where it used to be. So likely what happens here is conjugate addition of OH to the blue beta carbon to give you an enolate intermediate. And then we would protonate that enolate intermediate with some acid, perhaps enzyme, perhaps from water, and that will give us our product for these two steps. And that product, if you notice, is a form of citrate. We've just moved where the OH group is. All right, so this is called isocitrate. And I haven't shown you stereochemistry there. The stereochemistry is known, but it's not going to be important for us. But look at isocitrate. It is now an alpha hydroxy acid, and it's also a beta hydroxy acid. And if we were to oxidize that to the ketone, we are primed and ready for our decarboxylation methods. So pay attention to the chemical logic. I mean, it's really beautiful. We're going to a place where chemically we can get rid of CO2. All right, see you on, today's Wednesday, Friday.